let's share screen. So hopefully share screen works better today than it did the other day. Very good. Okay. So today I want to wrap up the computation for the anharmonic oscillator. And remember, what we were trying to do was start off with the simple harmonic oscillator, the quantum harmonic oscillator, and introduce a quartic perturbation to that harmonic oscillator. And I said that the point is that the quartic perturbation, where we add an x to the 4 term, makes the problem much more difficult to solve. And so we have to resort to perturbation theory to solve it, the same way we did for that one-dimensional integral. And we played around with the problem and came to the point where we needed to compute the classical solution of the equations of motion, or rather the solution of the classical equations of motion. And I said we were going to use the method of Green's function, largely because we're going to need to do that once we go to quantum field theory, where we have fields instead of position variables. And so it's worth setting up the problem. Okay, so I hope you can see the philosophy that I'm trying to build here. To give you the conceptual background for what we need to do and build intuition for what we're trying to do here, we worked out a single one-dimensional integral, which for a certain value of the parameter lambda, we could solve exactly. We then looked at perturbations away from lambda equals 0. And I said that the reason we're doing this, even though I know you can do it in much quicker ways, is to build up the formalism. So now we're exporting that formalism to a quantum mechanics problem, the simple harmonic oscillator and its perturbation, to the anharmonic oscillator, and we're going to try and play the same game there. And then once we've done that, we're going to move to the quantum field theory. And the reason why I'm doing this in a string theory, topical string theory course, is because, as I said way back when, there's a point of view in which you can look at string theory, namely as the fields living on the world sheet of the string, in which it is just a two-dimensional quantum field theory. So it makes sense that we understand what goes on with quantum field theory in a deep way before proceeding on to anything that's fundamentally stringy. Okay, that's one motivation. The other one is that quantum field theory is just one of the best things you'll ever learn. So let's continue then. I said that we're going to use the method of Green's functions to solve the classical problem. And you'll recall that the classical problem we're trying to solve is the harmonic oscillator equation, the Euclidean harmonic oscillator equation, which is why there is a minus sign here and not a plus sign, as you would expect for the harmonic oscillator. And to solve it using the method of Green's functions, what we do is solve the associated equation that the Green's function satisfies. And the Green's function satisfies the same equation of motion, except instead of having a source term, a forcing term on the right-hand side, we have this delta function. So this is a statement that the Green's function is really kind of a response of the system to an impulse, a delta function, a single kick that you give the harmonic oscillator, and you ask, how does the system respond? Well, it responds according to this Green's function. The Green's function satisfies the same boundary conditions that the original equation satisfied. So in this case, G vanishes at both boundaries, 0 and beta. And you can solve this using whichever method you want. The easiest thing to do is to go to Fourier space. So you do a Fourier transform. You get an expression for G of K. You then use an inverse Fourier transform to write down an integral representation for the Green's function. So all of this should be familiar. If it's not familiar, I'd advise you just revise quickly how to solve differential equations using the method of Green's functions. Now, what do we do once we have this solution of the classical equations of motion? Well, once we have that, then we can go ahead and play the same game that we did for the quartic integral that we did earlier and write down an expression. So following our earlier analysis, we can write down an expression for the Euclidean propagator. And I'm leaving out the dependencies here because it's clear, and you can go back to the lectures from previous, you can go back to previous lectures to see what exactly I meant. But this is given in terms of k naught, at lambda equals naught, minus the first order in lambda term, which enters like lambda over 4 factorial, times an integral. Remember, this came from Taylor expanding an exponential, times an integral over, let's say, tau of delta by delta j of tau to the 4, which means 4 applications of this functional derivative on k e naught of j, and then I evaluate all of that at j equals naught. Sorry, let's go back there. Okay, so this is just to first order. Of course, there are higher order terms which involve more derivatives, but you'll see that just doing 4 derivatives is sufficiently exciting. Any questions?
No.
Okay, so since we're taking 4 functional derivatives and then setting j equal to 0, the only part of this Euclidean propagator, the sourced Euclidean propagator k e naught of j, that will contribute is the one that's quartic in j. Specifically, if we expand the exponential, so if we expand the exponential so expanding the exponential, we get an expression for k e naught of j as some constant times a half integral with respect to tau, integral with respect to tau prime, j of tau, g of tau, let's write down tau prime, j of tau prime squared plus some other irrelevant terms, in the sense that they're not going to give us any contribution. Now, to make our lives easier, at least not computationally easier, but notationally easier, and for those of you who've done quantum mechanics, you'll know that inventing, developing the right notation can often make things significantly easier than working with cumbersome notation. I'm going to invent some notation here. So that's what 3 lines mean. It's a definition, if you want. J1, G1, 2, J2. So I'm taking the same expression that I had there, throwing away the irrelevant terms, and writing the term that's squared in the brackets as follows: J3, G3, 4, J4, where this object, an object like this, more precisely, something like J I G I J J J is my notation for the integral over tau I, tau j, j I of, j of tau I, g of tau I, tau j, j of tau j. Okay, that's just the notation that will help us facilitate this discussion. So with this, we then have a full expression for the propagator that we want, Ke. It is just C, the overall constant, 1 minus lambda over 4 factorial times 1/8 integral over tau, 4 functional derivatives with respect to j. In fact, I should be precise here, with respect to j of tau, acting on j1, g1, 2, j2, j3, g3, 4, j4, like such. And I'm throwing away higher order in lambda terms. So we're just considering terms to linear order in lambda. So how does a functional derivative act in this case? So to see how the functional derivative acts, let's consider a simpler object. So to see how delta by delta j acts on this object, I want to consider instead the quantity which I'll call x, say. And x will be 2 functional derivatives with respect to j of tau, acting on j, g12, j2. I'm just going to give you an idea of how the computation works, and then I'm going to leave it as an exercise for you to fill in the gaps. All right. So explicitly, this is 2 functional derivatives, delta by delta j of tau squared, acting on the integral with respect to tau 1 and tau 2 of j of tau 1, g of tau 1, tau 2, j of tau 2, like such, which is, now we can go ahead and act with the first functional derivative with respect to j of tau. Now, when I take the functional derivative into the integral, anywhere that there's a j of tau something, tau 1, tau 2, whatever, the functional derivative acts to produce a delta function. So there's one functional derivative outside, delta by delta j of tau. And on the inside of the integral, I have an integral with respect to tau 1 and tau 2. The first term has delta acting on this guy here, which produces a delta, which produces a Dirac delta function, delta of tau 1 minus tau. And then I have what's left over, g of tau 1, tau 2, j of tau 2. The second term is a j of tau 1, g of tau 1, tau 2, delta of tau or tau 2, say minus tau. It doesn't really matter because the Dirac delta function is even in its arguments as such. Okay. But if I look at this expression here, in the first integral, so this is two integrals, right? I can split up the integrand into two, so I can distribute the integral. In the first integral, I have a delta of tau 1 minus tau, and I have an integration over tau 1. The Dirac delta function, you will recall, is a sampling function. It samples everything else in its argument in the integrand at tau equal to at tau 1 equal to tau. Once I do the tau 1 integral, so when I integrate out tau 1, what's left is going to be just things involving tau and tau 2. Is that clear?
Yep.
Okay. And similarly, in the second integral, I replace everywhere I see a tau 2 with a tau. So the expression then is that this is equal to delta by delta j tau on integral with respect to tau 1 j1 of tau 1 g of tau 1 tau plus an integral with respect to tau 2 of g of tau 2 j2 of tau 2, which is, now I do the same thing, take the delta into these integrals, and exactly the same thing happens. So what's left out of this is an integral with respect to tau 1 of delta of tau 1 minus tau, g of tau 1 and tau, plus an integral with respect to tau 2 of g of tau 2 delta of tau 2 minus tau. Okay. The first integral samples tau 1 at tau, the second integral samples tau 2 at tau. Both integrals are going to give me a contribution that's just the Green's function. And so the upshot of this entire argument is that this is just 2 times g of tau. Okay. So you continue with this, and you'll find that, K Euclidean is just some overall constant times 1 minus lambda over 4 factorial times the integral with respect to tau of 4 factorial times g of tau squared. And I'm going to leave as an exercise for you to fill in the gaps in this. In particular, I would like you to see where the squared factor arises and where the 4 factorial factor comes from. This, by the way, is why when people talk about lambda 5 to the 4 theory, there's always a lambda over 4 factorial coefficient. So. In addition, I can now see why it is I didn't actually need to find a full expression for the Green's function. Why I didn't need anything more than the integral representation for the Green's function. It's because I don't actually need that full integral. Why not? Because G only enters, after I've done this, G only enters as tau tau. And if you remember the way tau 1 and tau 2 enter in the Green's function, it only enters in the difference between the two. So G of tau tau is really G of 0. So if I go ahead and do that calculation now, G of tau and tau is just minus 1 over 2m omega, 2 pi m omega, integral from minus infinity to infinity of dk over 1 plus k over omega squared. In particular, that exponential part has dropped out, which makes this into a simple one-dimensional integral that you can do. And the overall answer then is minus 1 over 2m omega. Okay. If I substitute this back, I will find that my expression for the Euclidean propagator, 0, beta, 0, 0, is just the constant times 1 minus beta lambda over 32 m squared omega squared, plus terms that are order lambda squared. And this guy, for lambda small, I can well approximate by an exponential. In fact, the exponential of minus beta minus beta lambda over 32 m squared omega squared. Okay, so maybe the order lambda squared and higher terms resum to an exponential, but I don't really care, because at order lambda, I can say that the expression in the round brackets can be approximated by the exponential. Why do I want to approximate it by the exponential? Well, because I really want to extract out of this thing the ground state energy, right? And if you remember, the ground state energy for the oscillator, or the ground state energy for a system like this, I get by taking minus the limit as the temperature goes to 0, or equivalently, the inverse temperature goes to infinity, of 1 over beta times, and here's the kicker, the logarithm of ke 0 beta 0 0. So this is where the logarithm comes in. Okay, so that's minus the limit as beta goes to infinity of 1 over beta log c minus beta lambda over 32 m squared omega squared like such. Let's go back here. So you can see that there's two parts to this. One part is beta independent, is beta dependent. This is this first part here. Okay, because when I multiply by 1 over beta, this part is beta dependent, but lambda independent. And so in the limit that lambda goes to 0, so there's no lambda sitting in here, there is a beta part, and I want to send beta to infinity. And if I want to know what that part is, I notice that it is beta dependent, but it is lambda independent. So in the limit that lambda goes to 0, this must just give the expression for the ground state of the harmonic oscillator, which we know is a half h bar omega if I reinsert h bar by dimensional analysis. So that's where this part comes from. Okay, so this is just the ground state of the, this just gives the contribution to the ground state of the harmonic oscillator. So we know what that answer is, right? On the other hand, this part, the correction to this, enters linearly in lambda, which cancels that piece off. And so linearly in beta. So this is in fact beta independent in total. Okay, so if I then write this out, and I don't want to go on to the next page, I'm going to erase this. I apologize for that. But this just gives me then the final expression that I want out of this, which is, and I'm going to reinsert factors of h bar as well. A half h bar omega plus h bar squared lambda over 32 m squared omega squared plus terms that will enter like lambda squared, etc. Okay. And I invite you to check then this expression against the more standard procedure of computing the correction to the harmonic oscillator that you would do by just expanding the exponential straight up. Okay, but this is how we do it using perturbation theory, and this is the key aspect of this calculation. And this lays all the framework that we need going forward for the more complicated quantum field theory argument. Any questions?
Not from me.
Okay. All right. So if there are no questions, then thanks very much, guys. And as I said, there's no lecture tomorrow and Wednesday. Tomorrow for AMM2 and Wednesday for topics in string theory. But I will record tomorrow's lecture a little later, and I will upload that, and I will record Wednesday's lecture on Wednesday evening and upload that. Okay.
Cool. Thank you.